Trigonometric functions are a class that we've skipped over fairly lightly so far in the course because we wanted to introduce them all together with both the derivatives without complicating some of the earlier properties of graphs and things like that. So for now, we're going to jump into a pre-calculus trigonometry review, or a study of trigonometric functions, and then we'll jump into how they work with the calculus rules and the derivative rules we've just been seeing recently. All right. So one of the things, of course, you should remember is the classic SOHCAHTOA rule, which is sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tangent is opposite over adjacent. That's the classic way to, or classic mnemonic for the ratios defined by the sine, cosine, and tangent functions when it comes to a right angle triangle. Hypotenuse, here's our angle, opposite and adjacent. Those particular ratios are handy when we look at some specific very common triangles, the 45-45 and the 60-30 triangle. The easiest way I find to remember the ratios in these triangles is just to build them as a standard on a unit length somehow. So for 45-45, or in calculus terms pi over 4, you can build a 1 root 2 triangle. And that lets you calculate things like sine of pi over 4 really easily, because sine is opposite over hypotenuse. And so opposite over hypotenuse would be the ratio 1 over root 2. Similarly, but with maybe a little more complicated, is the 30-60 triangle. You can imagine doing an equilateral triangle, each with sides of length 2. If we cut it in half, though, then we'd have two half sides, each of length 1. And if you bring Pythagoras into this, you'll find that this vertical side here has a length of root 3. That leaves you with a 60-degree or a pi over 3 angle here, and at the vertex here, you have a 30-degree angle or a pi over 6 angle. And that lets you calculate things like cos of pi over 3, which would be adjacent over hypotenuse, and if that's our angle here, pi over 3, adjacent over hypotenuse would be 1/2. Similarly, tangent of pi over 6, tangent is opposite over adjacent, would be 1 over root 3. So these triangles, the 45-45 or pi over 4, or the 60-30, pi over 6, pi over 3, those triangles appear fairly frequently, and it's good to be able to just do a quick sketch, because of course if you plug these numbers into your calculator and you get 1 over root 3, it's not going to look like 1 over root 3. It's going to be some complicated decimal, and sometimes it's easier to work with these exact values. Now, understanding the trig functions in terms of triangles is one thing, but those can be extended. It's helpful to do so because the angle that we can use in a triangle is really only 0 to 90 degrees, or 0 to pi over 2. And what we do is extend it by imagining the angle not just being from 0 to 90 degrees, but imagine drawing a circle and spinning around that circle and having the angle possibly extend out to these other points. And what we do if we imagine that is that the x-coordinate and the y-coordinate we get to will be defined by the x-coordinate by cos of the angle and the y-coordinate by the sine of the angle. So that's an alternative way to define these functions. If we do that, we can get a nice graph, because we can say, let's imagine the point here being theta equals 0, so we have this measurement here. And if the angle is 0 initially, the x-coordinate is 1. So imagine our position on this circle starting at 1. So let's put a value here. And if we cycle that through to 90 degrees or pi over 2, the x-coordinate at that point would be 0. So we have coordinates here of 1, -1 up here. So after one half cycle or quarter cycle pi over 2, we would have an angle. After an angle of pi over 2, we would have an x-coordinate of 0. After another pi over 2, we would have an x-coordinate of -1. And after another pi over 2, we'd have an x-coordinate of 0, and then we go back to 1. So adding some details here, pi, 3 pi over 2, we would get this classic shape of the function, of the cosine function. Again, we said that here already. Here's the graphical form of that. Cosine, remember, is the value or the function that starts at 1 and then goes down. And it would do the same thing on the opposite side here. If we had negative angles, which we can allow in the circle model, it'd be a little complicated with triangles, but we're allowed to do negative angles just counting backwards around the circle. If we use the circle definition, that would be perfectly valid, and we'd get a symmetric version here of the actual graph. What about the y-coordinate? Well, the y-coordinate initially, if we look at the height, how far up and down is it? It's at 0, then it goes to 1, then it goes to 0, then the height goes to -1. So very similar shape, not too surprisingly. It's the graph of the sine curve, loosely interpreted here in a manual sketch. Like so, and that would continue on as well here, like so. All right, and that would be the graph of sine of theta. It's worthwhile considering some of the ideas about identities that arise from those definitions of sine and cosine. One of the most commonly used ones in this course is going to be the property that sine squared theta plus cos squared theta equals 1. Well, the idea can be illustrated, or a sketch of a proof of that identity can be illustrated by thinking of the circle, picking any point you like on it, and then imagining drawing a triangle at that point. We always know that the hypotenuse is going to be length 1 because this circle is going to be of radius 1, so it's always one distance from the origin. And whatever this length here is, it's going to be defined by the location of this point, x and y. The length here would be whatever the value of x is, possibly absolute value. If we want to talk about a length, if x is minus 0.7, this length would be 0.7. But we just said earlier that the x-coordinate would be equal to cos squared theta, and that x would be equal to cos of theta, and y would equal sine of theta. If that's the case, from the definition of cos and sine in this particular circular model, we also know from Pythagoras that this is a triangle, and it's a right angle triangle. So the absolute value of x squared plus the absolute value of y squared will equal 1 squared. Well, we don't really need the absolute values if we're squaring, so we could just say x squared plus y squared equals 1 squared, which is 1. But these x and y's aren't random points. They're defined by cos theta and sine theta. X is cos, and y is sine. And so, just remembering what cos squared means, cos squared is simply a short form for exactly this, cos of theta all squared, as is sine of theta all squared can be written in short form as sine squared theta, and we have our identity. So starting from a Pythagorean triangle, right angle triangle formula, and recognizing that x and y can be interpreted as cos of the angle around the circle and y as sine of the angle, we get to the identity cos squared plus sine squared equals 1. Now, those are two so far completely different versions of our definition of sine and cosine, but it's not that hard to tie the two together. For example, if we draw any triangle in the right quadrant when everything is positive and everything's nice, we would have the x-coordinate at the point we're talking up here, and we'd have a hypotenuse of 1 with a right angle here. In this particular configuration, we would have any ratio we'd like to find. We said that x was equal to cos theta, and we want to maybe validate that. Well, let's go from the other way. Let's talk about cos theta being the angle here. Cos theta is the adjacent over hypotenuse. Well, what's the length on that side? That length is exactly x, and the hypotenuse length is exactly 1. So, yes, cos of theta is going to equal x. And likewise, sine of theta, which will be the opposite over hypotenuse, would be y over 1, which would be the y coordinate. So this length here is y. So whatever point we're at on the circle, the x and y coordinates can also be determined by the cos of the angle from the x-axis, and y can be computed from sine of the angle from the x-axis. So they are interchangeable definitions, especially in the first quadrant when everything's positive, and the circle definition lets us use negative values without getting into weird, what does that negative length on a triangle mean for us.